Hi everyone, welcome to our introduction to integrals video. We're first going to tell you what an integral actually is, and then we are going to see the difference between indefinite and definite integrals. Then we're going to show you the relationship between differentiation and integration, and finally give you a real-life example of the application of integrals. We have learned a lot about functions, but still one question remains, which is how we can find the area under the curve. Curves have a lot of different shapes, and so we don't have a set formula to calculate this. But we all do know how to calculate the area of this rectangle, which would be A times B. And what we can try and do is estimate the area of the curve using these boxes. So as you can see, we have tried to fit in these rectangles within the curve, but it is obvious that certain parts of the boxes remain outside the curve and some parts are missing within the curve. And so it remains a rough approximation. So what we do to make the approximation better is to reduce the length of dx, so thereby fitting more boxes within the curve. And as you can see, the approximation has already become better. So what we're going to do again is to reduce dx even further to better our approximation. As you can see here, the approximation has become even better. And this is what an integral does. It minimizes dx until it becomes infinitely small. And this is your basic notation. So you have your integral symbol and then your f of x times dx. And basically your f of x is your y-axis and your dx is the x-axis. So your integral represents the sum of all the boxes where dx is infinitely small under the curve. And what's interesting about integrals is that it keeps the idea of the boxes but gives you a continuous area under the curve. There are two types of integrals that you need to know about. One is indefinite integrals and the other one is definite integrals. If you look at the notation, they look basically the same, except for the definite ones has their boundaries written on the integral symbol. And what this actually means is that the indefinite integral takes a look at the full domain, as you can see in the graph, whereas the definite one takes only a part of the domain. So a certain defined part where between x equals 0 and x equals 10. And now we're going to look at how we actually calculate integrals. If we take a look at the function x squared, we know from going from x squared to 2x, the process is known as differentiation. And now there is an opposite process where you go from 2x back to x squared, and this is what we are learning as integration. So let's do this together, right? So if we have our function y equals x squared, we know that our dy by dx is 2x. And if we integrate 2x by dx, we come back to x squared. But what's going to happen if we have a different function which is similar? So if we have y equals x squared plus 1, our dy by dx is still going to be 2x because our constant disappears. And our integral of 2x is still going to be x squared. But we know that we have lost an original part of the function, so to get it back to x squared plus 1, we have to add a constant. So always remember when you're integrating an indefinite integral, you have to add a constant, which is very important. This is what indefinite integration looks like, and now I'm going to show you how we do it if we have a definite integral. So we're going to use the same function, 2x of dx, and now we put our boundaries, so we'll just say from 0 to 1, and we're going to get x squared again, but within this boundary. And because we're in this boundary, we don't need to add the constant. And then we substitute these values for x. So we have 1 squared minus 0 squared, which equals 1. And now I'm just going to show you on a graph what this actually means. So this 1 is the area under the curve between point 0 and 1. So this area is what we just found. When calculating indefinite integrals, here are some tips that you should remember. So you can think of your integral symbol as a track where this is the start and this is the end, and your lower number will always be at the start and the bigger number at the end. So when we were considering 0 and 1, you would write your 0 over here and the 1 over here. Then in step 2, when you write it in your brackets at the end, again this is just a projection of your symbol. So your bigger number will be at the top and your smaller number will be at the bottom. And then finally, when you're calculating it while plugging in these values for x, you do the bigger number minus the smaller number. And these are just some things you can keep in mind. Here we have a real life example of how integrals work. So if we look at this car moving, there are 3 functions that we can consider: the acceleration, velocity, and position at time t. If we take acceleration and we integrate that, we can find its velocity. And if we integrate that further, we can find its position. And as we just saw, differentiation is basically the opposite of integration. So if we differentiate its position, we are going to get its velocity. And if we differentiate its velocity, we will find its acceleration. And now we can see this in a graph. So if we start with its position with the function 2t squared plus 4t plus 1, and we differentiate that, we will find its velocity at 4t plus 4, and we differentiate that further, we get its acceleration of 4. And then when we integrate it, we get its velocity of 4t, and remember here we have the constant because we're looking at indefinite integrals. And then from its velocity we can go back to its position of 2t squared plus 4t plus 1. Now that you know how integrals work, you can look at our next video where we show you the actual calculations of how it's done.